Hello, everyone, and welcome to another wonderful day of PCAM. So today we're going to be exploring another method of describing real gases by building up the van der Waals equation of state. So last time we built up the virial equational form by taking the ideal gas law and more or less doing a power expansion. And this is essentially a brute force method of improving an equation that you have when you don't know what you're doing. Another alternative that we can explore is taking our ideal gas law and using chemical intuition to go ahead and improve our equation. So what we're going to do is start with our ideal gas law, so good old PV equals nRT, and we're going to really be exploring how we can correct our prediction of this pressure term. So if you remember, we have two major failures of assumptions in our ideal gas law. The first of which is that we're treating our molecules as hard spheres, with no volume. So the first thing we're going to need to do is include the actual volume that's being occupied by our gas. So where we traditionally just use the volume of our container, in truth, the volume that our gas has to move around in is going to be the volume of our container minus the volume occupied by the gas, which we're going to represent by the moles of gas times B. So B is going to be an empirical coefficient, so one that's determined experimentally, that essentially is a stand-in for the molar volume of the gas. And consequently, this means that this B parameter is going to be specific on whatever gas we're talking about. A larger gas, a larger B value. And it can be essentially thought of as liters of space occupied by 1 mole of that gas. Now, it's hard to know what this value is by first principles, so in practice, this is fitted experimentally. So what we can do is then input this volume term into our equation, and what we get is a first approximation modified gas equation, where our pressure is now going to be given by nRT divided by the actual volume that the gas has to move around in. And the first thing we're going to want to do is make sure that this form represents real experimental phenomena. And so the first thing that's going to show us is that if I have a larger gas molecule, so this means that my B parameter will be quite large, this will give me a relatively smaller numerator or denominator and a larger pressure term. And this is indeed what we saw when we looked at our real gases. Is the larger the gas is, the essentially larger the effective pressure is, or the more it tends to deviate positively from the ideal gas law. Additionally, we also see a similar phenomena that the more gas I put in for a given volume, so essentially the larger my N is, if V stays fixed, I'm also going to see a much larger pressure. And again, this is giving us a good description of the failure of the approximation of treating our gas as point particles. However, while this is a good starting point, we're still neglecting our second major approximation, which is the fact that it turns out that real molecules have attractive intermolecular forces. And so what this means is that my molecules are going to tend to stick together, which will reduce my pressure by essentially a value related to the strength of the attractive IMFs, which is going to be given by A, times essentially the frequency of interaction, which is going to be the square of the concentration of particles. Because don't forget, it's going to take two particles interacting to get a single interaction. And so the major feature here is going to be this A parameter. And this one is also going to need to be fitted empirically or from experiments. And it's really going to end up showing me the strength of my intermolecular forces. The more a molecule is attracted to itself, the larger the A parameter. And again, what we've already seen is that the stronger the IMFs, the more my gas is going to deviate in a negative fashion from the ideal gas law. So what we can do is uh, uh, illustrate this mathematically by taking my previous uh, equational form and essentially subtracting out the strength of the IMFs, or how much my gas will stick to itself. So this should also end up mimicking what we saw experimentally, which is the stronger my intermolecular forces, so the stronger my A parameter, the lower the pressure I'm going to end up observing. And this will also give me a Z value less than 1, which is again what we tend to see experimentally. However, it is also worth noting that if I increase the concentration sufficiently, I'm also going to reduce the pressure based on this concentration factor, which is again something we saw experimentally. If I increase the concentration slightly, it's going to amplify this intermolecular force term. If I increase the concentration even more, then this reduced volume term ends up dominating the equation. So this is actually quite a nice little equation. I'm able to take just two features that I observe experimentally and I know are failures of my approximations, and I add in some simple parameters that describe these failures. And with that, I get a fairly general equation with only two single parameters. However, it's worth noting that a lot of people don't like presenting the equation in this form. Instead, we like rearranging this equation in a more familiar form that looks more like our traditional ideal gas law form of PV equals nRT. And so it's often rearranged into essentially our modified pressure term times our modified volume term gives us our old friend nRT. However, it is worth noting that we often don't know the amount of gas present or the volume if I'm working in atmospheric conditions. So if I instead prefer working with size intensive properties, I can replace my N and V terms with molar volume. And this essentially can be done by dividing my whole equation by N. And when you do this, what you end up with is a reduced form where pressure is going to be equal to my strength of my IMFs divided by the molar volume times the molar volume minus the volume occupied by 1 mole of gas. So again, this is a nice, simple equational form that's going to be fairly general and relatively robust. So this does a very good job of describing real gas behavior, even under fairly extreme conditions. It also gives us several major improvements over our virial equation. The first of which is that I only need to use two parameters to describe an entire gas system, because these two parameters are not going to show any temperature dependence. So as long as I know what gas I'm dealing with, I can go ahead and look up these two values in, say, the back of your book or in a well-known table, and then I can describe the entire system fairly simply. However, it's going to not be quite as convenient for some of the mathematical analyses we're going to do later in the semester. But most notably, the biggest failure of the van der Waals equation is that it tends to start failing essentially below the critical point. So let's go ahead and take a look at the behavior of a real gas. So as we said before, if I've got a real gas under high temperature or low pressure conditions, I tend to be out in this regime, and I get fairly ideal behavior. However, as I start getting lower pressures and I'm approaching this liquid or supercritical phase, I start getting, well, some less ideal behavior. And it turns out that it's in this region that in this liquid coexistence region that our van der Waals equation really starts failing. Because it turns out that our van der Waals equation doesn't realize that our gas should have condensed into a liquid phase, because it's a gas equation, not so much a equilibrium equation. So as a result, if we try to apply our van der Waals equation to this coexistence region where some liquid is going to be present, we get something called van der Waals loops. And what we can see is, say, when I get below my critical point, so for CO2, this is 31.04. When I get below that, instead of seeing this flat line where my pressure stays relatively fixed, as my gas is now condensing into the liquid phase, instead what we see is something a little bit more awkward, as I expect my pressure to increase, and then I expect my pressure to decrease as my volume decreases. And that just don't sound right. So these van der Waals loops are essentially mathematical artifacts. And the lower the temperature you get, the worse this behavior is. And so it turns out that we can go ahead and correct for these van der Waals loops using something called the Maxwell construction. Now, this one's a fairly simple idea, which is the fact that you can draw a straight line through the van der Waals loops. So you find an equal area that's below the line and an equal area above the line. And this straight line should actually represent the coexistence region. Alternatively, you have to try and determine the boiling point for your liquid and try and draw a line there and go across. However, these can be fairly simple ideas in the abstract, but it turns out that it can be quite difficult to actually determine the equal areas in practice. So this can actually be quite a significant failing of the van der Waals equation, especially if I'm starting to deal with relevant low temperature, high pressure conditions where I might be having interactions in between my gas and my liquid, which may be very relevant conditions in reality. So this is one thing to be very cautious of when dealing with the van der Waals equation under these sort of conditions. However, otherwise, the van der Waals equation is fairly accurate, but there is some room left for improvement. So some people like to try and improve the van der Waals equation by essentially systematically adding additional terms or parameters to give us more information. So one of the simplest improvements is called the Redlich-Kwong equation, and it's more or less I'm trying to improve the description of the intermolecular forces. So I add in a temperature dependent into my intermolecular force interactions, as well as acknowledging the reduced volume. Now, it turns out the Redlich-Kwong equation is almost always better than the van der Waals equation. However, you may notice that it might not be quite so easy to use. This premise has also been continued with the Peng-Robinson equation, where you add in additional parameters. And there's also several other equations out there where you're able to start adding in 3 or 4 different parameters instead of the simple 2 of these three main equations. However, when we actually look at the data itself, we find that it's not really until we get to high pressure or high concentration conditions that we really need anything much better than the van der Waals equation. But if we do, Peng-Robinson generally gives us slight improvement, but under extreme conditions, the Redlich-Kwong equation is generally considered one of the best approaches to improving the van der Waals equation. But as I said, there is a plethora of advanced techniques out there. However, it can be difficult to sometimes hunt down all of the needed parameters. Which brings us to more or less the end of the van der Waals equations. But next time, what we're going to be trying to do is try and determine if there is going to be a good way to determine these parameters or to build a more general equation for a real gas. So next time, we're going to be talking about the reduced formula of the van der Waals equation. Till then, take care.